Hi, everyone, and welcome to day 9 of the summer school. And today we are talking about proof composition, which is, the missing component that we need to actually prove the celebrated PCP theorem. So it's quite exciting. And there's a nice story behind this proof. So originally, the proof of the PCP theorem was, it consisted of all of the components that we've seen, but after getting this, Reed-Muller PCP and Hadamard PCP, combining them together to get the actual theorem was a true tour de force, which required a just ridiculous amount of algebraic trickery and lots of clever ideas, which involved messy analysis in order to get it done. And years later, so people came up with a more clever way of, or rather with an abstraction, with this nice set of definition, which actually strip away all of the difficulties. And we'll get to see it, in a second. So what is proof composition? Why should we care about it? Well, so far we've seen techniques that achieved either, relatively short proof lengths and relatively large query complexity. So, the Hadamard PCP, where we have polynomial proof length, but polylogarithmic query complexity. And let me just mute everyone for a second. Good. So that was, very nice. And we did it using the Reed-Muller PCP. So when we took an assignment, we used the low degree extension of it, and also took a soundcheck protocol and put it there. Now the other part in the proof composition so the other type of thing we saw is the PCPs with huge proof length, with exponential proof lengths and constant query complexity. So this was, if you remember, the Hadamard PCP when we took, this linear encoding of the function, and we used it to encode the assignment and also the tensor of the assignment, and we got these two things. So we have colored in blue the good parameters that we'd like. We'd like to have polynomial proof length, and we'd like to have constant query complexity, but we don't want to settle for exponential length or polylogarithmic query complexity. Now the question is, well, how can we, how can we deal with that and get the best of both worlds? Okay, so as you can, imagine, we have proof composition. But what is proof composition? So we'll see that this is a nice technique where we actually take as a black box an outer PCP and an inner PCP, and we'll merge them together in a way that will inherit the length of the outer PCP and the locality of the inner PCP. So we'll want to take this Hadamard PCP, this Reed-Muller PCP, and use it as the outer PCP. So we'll get a polynomial proof length, and we'll want to have Hadamard as the inner PCP, so we'll get constant query complexity. Of course, it's more subtle than that, and we'll get to that soon, but that's the high-level idea. Okay, so, and just to mention that this leads to an extremely important result, which is called the PCP theorem, which shows that every language in NP admits a PCP, with the standard parameters, binary alphabet, soundness half, perfect completeness, of polynomial length and constant query complexity. And if you care that the Randus complexity is also logarithmic, which in particular, of log n, in particular, this would lead to this poly length. Okay, so what we're going to do after that is we'll see that we can also do an interactive proof composition, which would be to take the same type of ideas, but also apply them to interactive PCPs and interactive oracle proofs. So we can also, this would also be relevant to the other course of interactive proofs. And again, it's a way of doing it, and we'll see that in the interactive setting, this can be done much more efficiently than in the PCP setting, And it leads to some really optimal trade-off between proof length and query complexity that one can get using composition, as you will see in the other course. Okay, so let's see what is the high-level plan. And I think that the next two slides are maybe the most important one because they illustrate the idea. So as we alluded to before, we'll take, we'll have two ingredients. The first ingredient would be an outer PCP. That would be the shorter PCP with not an amazing locality. And we'll have an inner PCP, which will be really long, but it would have amazing locality. And we want to merge them together. Okay, so we just so we remember, oops. Yeah, so we have here good proof length and good query complexity. Cool. So how we will construct this new PCP? So there will be this following idea, which is we'll take the outer PCP and we'll think about it as the main PCP. So what do we have with PCP? We have a proof oracle, and then we want to make some queries to the proof oracle. So these queries, in this case, the query complexity is quite large. So we're making quite a bunch of queries, say polylogarithmically many queries. And then we want to check whether these queries, then the PCP verifier checks whether these queries are good or not, whether they satisfy, a certain constraint. And based on that, we decide whether to accept or reject. So instead of literally making these queries, we'll instead just, pretend like we'll have a mental picture of the locations where we want to make the queries. And then we'll have a PCP that will run with respect to the statement of whether this local view, which uses a lot of queries that I can't afford, whether would that be something that would be accepted by the verifier. So that's the high level idea, and let's try to picture it. So we have here the outer oracle. Think about this as, we start with some 3 coloring of a graph, and we encode it via the Reed-Muller PCP. So we got this polynomial sized PCP. And now what we want to do is to say, well, this PCP admits a verifier that would look at, let's say, these many points. So what we'll do is we'll want to look at the statement whether, querying this proof, the proof of the outer PCP, pi out, at these locations would be accepted by the verifier. And so, for every choice of random coins, this would lead to different queries. And then we'll have a different proof that would say, these queries that you see here, and here's a PCP for checking that they are valid. Right? So that's the very high level idea. And it's not a new idea in the sense that this is very reminiscent of code concatenation. So, in coding theory, for those of you who know, the first proof that we had of getting, codes which are symptotically good, and by that I mean they have, linear distance and linear length. So this was done using a similar paradigm when you take 2 codes and you kind of compose them together, but in the coding theoretic language, this is called concatenation. Okay, so let's try to see how to implement this high-level idea and see what will go wrong. So we start by computing. Let's see what the prover would do. We'll compute this outer PCP, P out. So this really, think about it as we have an NP assignment for a 3-stat formula or quadratic formula. We then get the Reed-Muller PCP or whatever PCP of our choice, and we write this thing down. Then we are enumerating over every choice of random coins that the prover might have. Based on that, we know which queries the verifier might make, and for each one of them, we'll compute an inner PCP, these guys here, which will kind of parameterize by just the inner proof with respect to a certain random string. And this would be with respect to, the input and P of out. Okay, and then we'll output as a proof this entire PCP oracle, which will consist of this thing and all of the little things. And now the verifier, instead, would just like sample some random coins. And based on that, it would check, it'd say, I sampled my random points. So I need to query this point, this point, this point, this point, and this point. And so in order to check the statement that these points are all good, I'm going to invoke a PCP for that statement. So I'll make this number of queries here, and essentially I'm done. Right, so this is the naive idea. And let me try to kind of like unpack why this make sense in terms of, length and locality and what it means, and then we try to see what breaks. So first of all, think about it, I want to get polynomial proof length. So it means that I can't start by, just 1 second, noise. Okay, so suppose I want to have a long PCP, so I can't start by encoding it with, the Hadamard PCP, which has exponential length. So I'm starting with the Reed-Muller one. But now my query complexity is too large. So I can't read what's written there. So I'm saying, let's verify this using a PCP. So I take this number of locations. Let's, for simplicity, say that these are log locations. And then I encode them using the Hadamard PCP. What would then be the proof length of an encoding of logarithmic bits using the Hadamard code? Well, it's like taking something which is roughly exponential and something which is log, then it would be, linear, or more accurately, it would be polynomial. So this would be, a polynomial length proof, and these would be polynomial length proof. And so roughly, in a high level, we might think that we'll, have just a bunch of these polynomial length proofs, and so that the total length would be polynomial, and all is nice and well. But then, what queries will we actually make? So we'll want to make these queries, but instead of actually making these queries, we'll only, we won't make the Reed-Muller queries, which there are like polylog of them. Instead, we'll use just the Hadamard queries using a PCP, and then we might get O(1) locality. So that's like the naive idea that one might, have in this setting. And yeah, and so I want to kind of like, to ask you two questions. Whether the two questions are, first, whether the high-level naive plan makes sense, and second is whether you see any problems with it.
The problem is that we never query this proof out, and that's clearly wrong. So we never check consistency between this outer proof and what this inner proof claims about this outer proofs.
Yeah. That's precisely the point, or at least one of them. But I want to kind of like to lay down, a bit more precisely, and I didn't really mean I didn't really say what I mean by invoking the Hadamard PCP here. So let's try to see, let's try to define things in more detail and see what breaks. So, that's a broken slide. So here's the first problem that we have. So, I kind of like hid under the rug and said, yeah, if you want to make the queries here, then just invoke the Hadamard PCP. And I said it really fast, so you won't really ask what I actually mean by that. But let's think about what is a PCP, right? So a PCP, you can think about a verifier, V. It gets some explicit input. For example, no, sorry for that. I'm ruining all of the suspense. Okay, sorry for that. So, let me try to do it again. So we have this verifier. Let's say that this is for quadratic equations. I don't know. So we get as input this description X of, a formula. And then we have this PCP oracle, which is an assignment to this formula. So what we do, we read the entire formula by ourselves, And then after we read the formula, we make, this small number of queries to the PCP. So if we were to do this thing using the Hadamard PCP, what would that mean? It would mean that we'll have to look at all of these points, this point and this point and this point and this point and this point. This would be our explicit input X. Read the entire thing, because this would define the problem, and then make a small number of, something keeps jumping here. I don't know what's happening. Okay. And then, okay, so just like to continue. So, and then we'll make, after we read all of these points, we'll need to make a small number of queries to the inner proof. And so we didn't really save on the query complexity here, right? So it depends on how you interpret what I said. Either you just make the queries to the inner PCP, but then it's like checking that a formula is satisfied without even knowing what the formula is. Or we have to read the entire thing. So that's a problem, right? We wanted to save on query complexity, and this doesn't happen. So the idea to fix it would be, maybe we can somehow make small number of queries, both to the proof and to the statement. So in this setting, just to kind of like highlight, the original proof is now the statement that we want to verify using a PCP oracle. So I don't want to make only like small number of queries, constant number of queries to the to the proof that the outer proof is correct. I want to make constant number of queries here and constant number of queries there. Let me know if does this make sense, if the problem is clear. And also if you might have any idea how like what type of idea we already saw in the course several times, which type of relaxation we can have that would allow us to not read the entire input. Right, remember we said that there are two main leitmotifs that we keep using, and we saw it a lot in the first lectures. So I agree that making random linear combinations often works, but here I actually talk about this notion of property testing. We had a function, we wanted to check that it's linear, but we didn't want to read the whole thing. So we did this testing of like accepting if it's, exactly a valid, exactly linear function, and rejecting if it's far from a linear function. And so similarly, we can have a notion of a PCP of proximity. And a PCP of proximity, it's kind of like property testing with proof. So let me kind of try to illustrate what this means, right? So what we want is that each of the inner PCPs, it wouldn't be, a proper PCP. It would be this new notion. And the way of thinking about this new notion is as follows. We'll have this, actually, I think I have a nice drawing. So, okay, this is to say, like, before we had this verifier, and it got X explicitly, and it made queries to this PCP, just a small number of queries. So what we want to do is to not give the verifier X. Instead, we want to write X as another oracle and make, constant number of queries to this thing. And then what we'll do is we'll accept if this is a perfectly valid statement, and reject if it is far from a perfectly valid statement. Okay? You might ask, why would it be the case that the problem that we have would be, why is it okay to only look at these two cases? And we'll see that we'll have to deal with that as well. But that would be the idea. If we want to check a problem without even reading it entirely, then inherently we have to reduce to some approximate decision problem. And that would be our plan. Okay, so, And let me kind of like make it more explicit. What is the statement that we are going to check? So the statement would be the following thing. So, suppose that we fixed some random coins. And now this means that I only look at these particular locations. So let's write them down as a new vector. This is just like the local view of the outer PCP verifier. We say, suppose I use this randomness, I make this random query, so this defines like a local view of the object. So I now define this to be the new object. I call it X, and I want to ask whether this new object is something that the verifier algorithm would accept, whether this is an accepting local view or whether it is, far from being an accepting local view. And suppose that we had this like nice feature that somehow, all local views are either perfectly fine or far from fine, then, then maybe this should work. So that's the high level idea. But of course, this leads to the obvious problem that we cannot hope that this would be the case. Like, I mean, we cannot hope to solve a property testing problem unless we are fine with having this distance, unless we have this guarantee that either this is a perfectly valid local view, or it is something which is extremely far from being a perfectly valid local view, right? Because it could be the case that, if I'm only looking locally, then I could be here and then like no local algorithm could work, because it could be that the only coordinate that I didn't read is the coordinate that would make the difference. And so the solution to that would be to have a PCP, that the outer PCP would be a robust PCP. So what is a robust PCP? It's exactly the condition that we need. It tells us that, if the PCP oracle is, if the statement is far from being, if the statement is incorrect, then the local view either would be an accepting local view, or it would be something which is very far from an accepting local view. So and then like this could make sense, because we say in this situation, we'll have this outer proof. We'll take some random coins. This would restrict our attention to some, local view. And then we know that this local view is either perfectly valid or far from valid. And if it is perfectly valid or far from valid, then this is a testing problem. And then we can use a proof of proximity where we only make, small number of queries to this thing and small number of queries to this thing. And we decide whether it is perfect or far from perfect. And now we have the guarantee that we are not in the, gray zone or brown zone in this case. And just to say that the reason for optimism, why one can expect this to happen, is because, well, remember our dear old friend, the Reed-Muller code. So we showed in the low degree testing that in fact, if the code is far from, if we take a hypergroup which is far from being a low degree polynomial, then any line would be far from being a low degree polynomial. So this kind of like tells you, this is like a combinatorial example of robustness, right? Think about it. It tells us that, if the global object is corrupt, then any structured local view of it, and here the local view would be just a line in the cube, then this line would also be roughly with the same proportion of corruptions. So any questions regarding the problems and the suggested attempt for solving them? Okay, so let's continue, and feel free to stop me at any time. So what we'll do now is go over these two components and do them, define them slowly and carefully in a way that will make sure that all of the things I said, now, with hand waving are concrete, and then we can show how to compose and get this PCP theorem. So let's try to zoom in first on robust PCPs and see how we can make them. So how we can define them. So what would be a robust PCP? So first, for simplicity, we'll start with non-adaptive verifiers, just to make our life simpler. So what does it mean, a non-adaptive verifier? It means that I'm not querying a certain location, reading the value, and based on that, choosing another coordinate. No, I'm not doing anything of this sort. I'm flipping coins, and based on these coin flips, I'm choosing locations. So that's what I mean by non-adaptive. And this is typically the case. It's like what we had in all of the positive constructions. So it would make our life easier. So now let's see how we can describe our algorithm where we have a verifier with oracle access to a proof, an explicit input X, and some random string row. So we can describe this, the way that the verifier operates, we can decouple it into two parts. In the first part, the algorithm will choose a query set Q. That would be the local view, the set of queries that we'd like to make. And then it would query the proof in this location, query the proof pi in the locations Q, which are affected by the explicit input and the randomness. And then we'll have a decision algorithm which gets this entire local view, and based on that makes a decision. Right, so if you think about what we did so far, then the query set of let's say the Hadamard tester, it's just a triangle. So you can think about an algorithm which chooses a triangle, this is Q, and then runs an algorithm which rules with respect to the three values of the triangle. So nothing fancy going on here. And then we want to define just the relation of all accepting local views. So the definition looks a bit long, but it just means that the simple thing that these are all local views that would make the verifier accept, right? So I'm saying, given an string X, input X and randomness row, then this would be an accepting local view. So this is just anything that we'll get at the size, like any possible assignment to the queries, to the local view that we want, that would make the decision algorithm accept, right? So that's a notationally, accurate way of saying this is an accepting local view. Does this make sense? Any questions regarding what is a local view and what does it mean to be accepting local view?
So we assume that this decision is deterministic.
So no. So typically it would be deterministic, but just to say here, when I'm writing D, notice that it gets as input X, it gets the assignment to the local view, and also the random string. So maybe we make this decision using randomness, right? We just, for the sake of generality, we don't want to restrict it. Though in practice, I don't think we'll actually use it. Okay. So what is a robust PCP? So we say that a PCP would be, a robust PCP with some parameter sigma, if the following holds. So we'll have the exact same condition of completeness. So it means, given some X in the language, there exists some proof such that we will accept the proof with high probability. Nothing new here. And then we'll have this notion of robust sounds. So, it's like a long equation, but what does it say? It tells us that if we have an input which is not in the language, then for any malicious proof we might get, then with with very low probability, we could be in the case that that we will accept if the distance of the proof, when we look at it in local view, and we look, okay, so what do we do? We look at the distance of the proof, of the local view of the proof, from the set of all accepting proofs. And we're saying, the probability that we will accept will be tiny. If, so we say that, not only that the probability we accept will be tiny, but also the distance between the proof and the set of all accepting views would be large. So this was a bit confused. Let me say it again and also do it with the diagram. So I'm saying, I have a bad input and a false proof. So, I have this like, this is, some false proof and it's far. Now I'm saying any local view that I will make to this proof must be far from an accepting local view, except with some small probability. So that's the idea of robust soundness. And notice that if I'm like, taking the robustness parameter and setting it into 0, then we get exactly the definition, the standard definition of soundness, because it just tells us that either it's like, perfect or it's not exactly the same. So it might differ by a single point. So that's like the idea of a robust PCP. And again, I just want to reiterate, the thing to remember is to say, when I'm doing these local views, I know that either I see if it's a valid input, I will see a perfectly valid local view. And if it's a bad input, I will see something which is far from being a local view. Now, and you might say, this seems, how can one make such a thing? But notice that if we use any PCP, which is itself a code, like polynomials and things of this sort, then it kind of tells you that, two objects must be pairwise far. And so any two local views should be very far from another. And this is also how, like, we'll see that we actually construct this kind of thing. Okay, so any questions regarding robust PCP before I continue to the second component, PCPs of proximity? Good. I think this should be fairly clear. And yeah, so just I see some questions in the chat. So yes, Q returns the positions that we want to, the indices of the positions that we want to reach from pi. And let me go back so I see questions regarding A. Let me see. Yeah, and A, kind of like think about it for answers. So it's like the answers to these queries. And yeah, so let's see. What does sigma to the qx? Okay, so let me clarify this definition because it's a bit confusing. So what I'm saying here is the following thing. Sigma is the alphabet of the PCP. So I have a PCP oracle, and each element here, it's like some element of sigma. So I have, this would be first element, second element, 4, 5, 6, and 7. So Q would be some set of queries. Let's say I want to query location 1, 3, and 5. And A would be whatever field element which is written here, here, and here. Yeah, and it could very well be the case that I'm using Q twice, one as the number of queries, yeah, okay, so I see. Oh, I see. Indeed, there is an overloading where Q is sometimes the number of queries, and the other time it's the query set. So I'll sometimes make this abuse notation. Yeah, you're right. So, alternatively, I could fix it by doing this. Are you happy now? Good. Okay, perfect. So now let's continue to the second component, PCPs of proximity. And that's actually like proof of proximity. It's one of my favorite topics, one to which I dedicated a lot of time. And the way I like to think about it is like really think about a testing problem, like linearity testing or low degree testing or any other testing problem. And now try to augment it, like think about how a PCP would look for such a testing problem, right? So, so a PCP, what does it mean? It means that we want to prove for some given instance and some witness that the witness is close to a valid witness. So, for example, if I have an equation, that's the instance, and an assignment, that's the witness, then I want to prove that an assignment is close to a valid satisfying assignment. So the picture to have is maybe, we have a verifier, and the verifier gets an assignment. So the verifier knows X, it knows the description of the equations that it's trying to check, and it gets some assignment, which is, plug in the certain values to X, and this is what we want to check, whether this is a satisfying assignment. And then the prover provides us with some PCP oracle. The verifier makes queries both to the assignment and to the proof oracle. And based on that, we are deciding whether this is an accepting assignment or something which is far from an accepting assignment, right? So notice that crucially, the queries and the query complexity that we'll count is not just query complexity to the proof, but both to the input and to the proof. Okay, so think about R being some binary relation, and to instantiate it so it won't be too abstract, think about X as a formula and W being an assignment to the formula, a witness. So we can define the language of this relation as being all instances for which there exists a witness, right? In an equivalent way, just to kind of to articulate it, this would be the set of all formulas such that there exists an assignment that is a satisfying assignment. Okay. So now what's happening is we want to look at what are the valid instances of X, right? We'll denote by R of X the set of all witnesses that belong to the relation, right? So what does it mean? It means in this example of equation, these are all of the satisfying assignments, and the set of all satisfying assignments. And notice that this could be, if this is a not satisfiable equation, then it could be that the set of satisfying assignment is the empty set because there is nothing that would satisfy it. And so the testing problem that I want to kind of to think about is that R of X is the set of all satisfying assignments, and the no inputs would be everything which is far from being a satisfying assignment. And then what would be a PCP of proximity, which we just refer to as PCPP of proximity. So it's a system for this relation R with this proximity parameter delta that would satisfy these two conditions. The first condition would be the standard one. It tells you that, if you get if you get this access to some, input X and witness W, so to an equation X and an assignment, to a formula X and an assignment W, then there would exist a proof that would convince the verifier with probability 1. And here the interesting part, it means that if we have some X and W, some formula and assignment, such that this assignment is delta far from being a satisfying assignment, then for any possible proof, malicious proof that could be, I will accept with a tiny probability, just with this probability of error. Okay, does that make sense? And thank you, Yotam. So Yotam is asking whether the distance to the empty set is 1. And the next point in the slide says that we'll use as a convention that if we have an empty set, then the distance will be 1. Yeah. So this is why. So thank you for that question. Okay. So these are PCPs of proximity. And in fact, these are these two notions. And we'll see that using these two notions, we can get the best of both worlds and do the previous attempt that we had, but now everything will work perfectly. So let's see how we do the composition. As before, we have two different components. As the outer PCP will have some PCP for language, but this would be a robust PCP. So the outer component would be a robust PCP. And think about this as, a robust PCP with great proof length, but bad query complexity. And for the inner PCP, we'll have a PCP of proximity with amazing query complexity, but maybe the length is large. And so we'll define the PCP composition exactly as before, only now we'll be a bit more accurate about what we mean. So again, we'll write down the proof of the outer PCP. This would be, for example, the Reed-Muller encoding of a satisfying assignment. And then we'll look at every choice of random coins. This would dictate a local view. And we look at this local view and we'll provide a proof for each possible local view saying this local view is an accepting local view. So let's do it, a bit more accurately. What's happening? We have our prover. The prover computes the outer PCP. It then enumerates over all possible random choices that the verifier could have. And it provides a PCP of proximity for the statement that the local view that is induced by these random choices is an accepting local view with respect to the verifier. And then it writes down this proof here. So the entire proof would consist of the proof of the outer PCP plus the proof of the inner PCP with respect to each possible local view, or alternatively with respect to each possible choice of verifier randomness. And the verifier would just choose randomness. And then all it would do, it would invoke the inner PCP with respect to the local view. So, it chose the randomness. Then it knows that the local view consists only of these points. So it's kind of like thinking about these points. And this is the new thing that we want to check using the PCPP. And we would run something that would make a constant number of queries to the inner proof here, and constant number of queries to the inner proof here, and that's it. And the beauty of it is that the moment that we have these like two simple definitions, soundness is just a trivial 3-line argument. So let's see what's the argument, and hopefully this will be quite convincing. So we're saying, completeness, of course, everything will hold as before because we had no problem. In terms of soundness, suppose that we have this X which is not in the language. So think about, formula which is not satisfiable. So we're saying that except for this small soundness error of the outer PCP, the local view that we will look at would be far from an accepting local view. Why? Because this is a robust PCP. This is a false statement. So we know that not only will reject most local views, like the local view must be far from an accepting one. But if it is far, then we know that we have a PCPP which can distinguish it something which is perfectly valid or far, and then it would accept. And that's it. And the soundness error would be just getting both the soundness error of the outer PCP, because it might be the case that we just chose the wrong local view here. But it can also be the case that we chose the wrong local view and we're kind of like querying these things. That's it. And that's the entire composition. As always, stop me if something is not clear. And this leads to the PCP composition theorem. So I'm just going to wrap it up and just kind of like say what we get. So what do we get? We get that, we get a PCPP with soundness error, as we said, that gets, just the addition of both of the soundness error of the inner and outer, because we're running both of them. It would have random complexity of that of the inner, of the outer plus the inner, because again, we're running both of them. The proof length, so this is important. So it means, what would be the proof length? It's the length of the outer proof. And then for each choice of randomness, it would be the length of the inner proof, right? So we get this like big block in terms of the randomness. So we have to be careful with that. And similarly, you can check that the prover time is proportional to that. And the query complexity is just the query complexity of the inner PCP, because this is the only thing that we're going to look. This is like the only query that we're actually making. And the verifier time would be the same as the inner verifier, because that's the true verification that we are doing. So the next thing is I'm going to show you how we use this composition theorem to prove the PCP theorem. But let me I see that there are some questions, so let me skim over the chat. Okay, so regarding of whether we need some consistency check, then actually we don't, and the reason being is, we kind of go to the previous slide, because we're implicitly doing a consistency check here. So the point is that like the PCPP implicitly refers both to this oracle and this oracle, and it only accepts valid pairs. And so this is not a problem. And now, now I see that you said never mind. The second question is about whether we're going to get rid of the non-adaptiveness, and we'll keep it for now because everything is much simpler, and like no construction actually that I'm aware of makes use of like adaptiveness. So we'll leave that.
I didn't mean can we get rid of it. I meant I don't understand why this is non-adaptive, because I feel that like the queries that you make to the inner proof depend on the queries that you make to the outer proof.
No. So what I'm doing is the following thing. So so I'm defining the PCP. So first of all, I only said that like have a non-adaptive PCP here, like for the outer PCP. So this is this thing. So it means that we're verifying everything by checking some points. So I didn't refer to the inner PCP, but in fact, one can even design PCPPs where you just choose 3 locations at one point and 3 locations at other point, and you can fix them in advance without checking what's happened. But this I didn't describe or show anything of this sort. Okay, and I also see that Tal answered that in the chat as well. Okay, thank you. Good. So excellent. So now what I want to do is kind of to sketch how we actually prove the PCP theorem. And we will just, I'm going to lie a little bit just to, or at least hide some, not hide, but skim over some details, because there are a lot of small technical ideas, but I kind of want to give you at least a sketch of what's happening. And anyone want to give it a shot, with respect to what we had, how would you approach, assuming we know what we know, how can we show that any language in NP can be verified using a polynomial size PCP and making only O of 1 queries? How would you approach it?
So basically we have to prove that this so that the second PCP that was on the lecture, this with low degree, can be lifted to a robust PCP, and that this Hadamard PCP can be somehow lifted to the proximity PCP, and then we just compose them and we are in. Yeah, and in fact, just to not ruin the suspense for the rest of the listener, because Tal also got an additional point that so let me just say it. I see all the answers are already there in the chat, but let me do it explicitly anyways. So thank you. Yes, you're all very right. So we'll do it in 3 steps or 4 steps. So the first thing is that the Hadamard PCP, we can actually view it as we defined it to be a PCPP, but we need to do a shift of perspective. So we call it what we had in the Hadamard PCP. We had as input quadratic equations, and then the prover provided us with some assignment, and we only made constant queries to this assignment in order to check, in order to verify this is a satisfying assignment. But now think about the Hadamard PCP as a proof of proximity for a different problem. In that different problem, the assignment is the input,
And the rest of the PCP oracle, this encoding of the low degree extension of the quadratic terms and the other terms, this is the additional proof. And so if the problem that we want to check is not a satisfiability problem, but rather just testing whether an assignment is valid or not, then this is exactly what the Hadamard PCP is doing, right? So let me say it again. In the Hadamard PCP, the input was the description of an assignment, and the goal was to check whether there is something that was satisfied. And then the prover provided us with the assignment and its Hadamard encoding. So we can just alternatively think about, the formula being a parameter, which is completely known to all parties. And then the instance that we want to check is whether a given assignment is satisfiable or not. And the proof for that would be, all of the Hadamard encoding that we've used. So in fact, the Hadamard PCP can be cast with essentially no changes as a PCPP for, instead of like satisfiability problem, for evaluation problem. But if you think about it, what we want to do, we want to check whether a view is an accepting view. So it's indeed an evaluation problem and not a satisfiability function. So we actually have this PCPP. And then we can also observe that the Reed-Muller PCP can be made robust. And why can it be made robust? So remember that I told you that, we know that we showed in the low degree testing that the tester for the low degree test itself is a robust test. Why? Because we said that if the entire cube is far from being a low degree polynomial, then each local view, each line would be far from being a low degree polynomial as a univariate polynomial. So in some sense, the Reed-Muller PCP, what does it consist of? It consists of, the low degree extension of an accepting assignment. So this is an encoding, proper encoding of the Reed-Muller code. So it's a, low degree polynomial. And so this thing must have distance. It must be robust, but it also includes the sum check protocol. And if you think about the sum check protocol, it's also consisting of this bunch of polynomials. So there is an additional step, non-trivial step, that one has to bundle all of these polynomials in a way that you get just one polynomial. So you can argue that like this also, that the bundle polynomial is also, that the polynomial is also a complete low degree polynomial, but this can be done, and one can bundle together all of these PCPs and get robustness this way. And so there is a problem that was written in the chat and was carefully identified, I think, both by Tal and by Erken. And the point is that, well, I kind of, let's think about the setting of parameters. So, if we had a proof of length linear and the local view would be logarithmic, and then, the encoding by Hadamard would take it into something which is polynomial length, and then we had like very small query complexity, and this would yield a polynomial length proof. But the point is that if we really look at the parameters, the exact parameters of Reed-Muller and Hadamard, and we do this composition, so by that I mean we look at we look at a proof of size which is kind of like doubly exponential as because you also, the Hadamard encoding it's not just the Hadamard code of the assignment, it's the Hadamard encoding of the tensor assignment, so it's like exponential in x squared, and we're making polylog queries, and we look at the randomness complexity, and we're paying 2 to the randomness complexity times that, then we actually get something which is of quasi-polynomial length, and not what we want. And the solution, which Tal wrote in the chat, is that we need to compose twice. So, we'll take a Reed-Muller PCP, we'll compose it with an inner PCP, with a Hadamard PCP, and we'll get this composed PCP, and then we'll compose it again with, so we'll make like, we make like these two compositions, and then we'll actually get the one that we need. However, as Erkan wrote, that there is a problem here. And the problem is that, we started with robust PCP as the outer PCP, and then inner PCP was PCP of proximity. And so it's not clear whether we're preserving robustness or whether we preserve proximity, and things of this sort. And the point is that if both of the components are both robust and PCPs, then we preserve both robustness and like being proof of proximity. And so in fact, what we know is we can actually make both the constructions robust PCPs of proximity, and then we compose the robust PCP of proximity with a robust PCP of proximity, and we get a robust PCP of proximity, so we can do this as many times as we'd like. So that's the whole idea of the composition and how we get the PCP theorem. Feel free to stop me with any questions, and if not, I'll spend 5 to 10 more minutes to tell you how proof composition works in the setting of interactive proofs and why it's it's more efficient there. Okay, so now we have IOPs, which is a multi-round PCP. So in each round, the approval is sending us another PCP oracle. And it's a simple exercise to define robust IOPs and IOPs of proximity just by taking the standard definitions and then modifying as we did. Right, so what would be an IOP with robustness? Well, the completeness condition would be exactly the same. If it's a valid input, then the probability that the protocol would accept would be high. And this robustness condition would change almost exactly as in the setting of PCPs. So we're saying, if we have a bad input, then for every approval strategy, then, the distance of the of the local views, the point in which we look in the oracles from accepting local views must be large, or the probability that it will be small is small. And the only thing which we need to look at is that we're looking at the concatenation of all of the oracles. So we're looking at the distance from all of the oracles. What you do is each line round you get a PCP, so you want to look at the distance from all of them together. So that's the only thing we should do. And what would be an IOP of proximity? So an IOP of proximity, it would be a system with some proximity parameter. The completeness condition is what you expect. If I'm giving you a formula and an assignment, and satisfying assignment, then we will accept with high probability. And on the other hand, if we get an assignment which is delta far, then we will reject it. So we know exactly the same type of statement. And I want to ask you a question, which is something it's whether you can think of any IOP of proximity which we've already seen in this course.
FRI?
Yes, exactly. So thank you. Exactly as we saw in Fry, if we set this abstract relation to be just to read Solomon code, all univariate polynomials of low degree, then the Fry protocol is exactly an IOP of proximity. Why? Because we are making a small number of queries to the input, which is the function that we want to test whether it's a polynomial of low degree or not. And we're also making a small number of queries to each one of the proof oracles that the prover is sending us. And at the end, we're either, saying, is this a perfect polynomial of low degree, or is this far from polynomial of low degree? So this is an example that we've already seen. And I want to conclude this lecture by just saying what happened with respect to interactive proof composition. So everything will be exactly the same, only we'll pay less. And what's the idea here? So again, we'll have two ingredients, this, non-adaptive, robust IOP is the outer IOP, and the inner IOP would be an IOP of proximity. And we'll have a new composition. And what would be the new, like, what would be the composition? So the verifier would start by taking some, like, sampling some random string. And then, you know, what we'll do is we'll kind of like look at the interactive part of the, wait, I think that, like, yeah, it would be easier to kind of say the following thing. So what we'll do is we'll sample a random string and we'll have the interaction of the outer PCP. So what happened in the interaction of the outer IOP? So, you know, it's like the prover is sending an oracle and the verifier replying with some of the randomness, and the prover throws again some another PCP and we reply with some more randomness. No queries are made so far. Then the interaction part terminated, and now we want to do the composition. And the point is that we no longer need to run the IOP for, like, the prover doesn't have to send us the inner IOPP for each possible randomness. Why? Because the interaction between the outer protocol already completely terminated. And so at this point, the verifier could just say, well, you know, here is what was once my secret randomness. And now, given that, send me just the inner PCP that I need. That's the inner, it's like the inner IOP of proximity that I need. Right? And notice that, you know, at this point, the prover can do nothing because he already committed to everything. And by this point, the soundness guarantee that we have is already guaranteed with respect to the randomness. And so we can give everything and just like reveal everything to the prover, and he has nothing to do except sending the relevant inner IOPP. And yeah, and so what does it give us? So it gives us another IOP. And the soundness error would be as before, the soundness error of, you know, the outer one plus the inner one. The round complexity, which is new, it would be, again, we run one time the outer IOP and one time the inner IOPP. And the randomness complexity, again, because we're choosing the randomness in both of them, so just like everything behaves additively. But here's the crux. And the point is that the proof length, well, before it was the length of the outer proof plus 2 to the power of randomness times the length of the inner proof, now it would just be 1, because we're not, the prover doesn't have to send everything for every choice of randomness, but rather for the one choice of randomness, which we actually specified. And this makes a dramatic saving, and it's part of the power of IOPPs. Yeah, and the query complexity remains the same. Okay, so that's everything that I wanted to say. Tomorrow we'll see how we can take such IOPs with, you know, nearly optimal parameters and actually compile them to cryptographic proofs and kind of get, you know, using crypto, amazing like short proofs, which would still have, you know, all of the benefits that we have. And we'll also see some other applications, including hardness of approximation. Okay, so I'll stop the recording and I'll be happy to stick around and answer some questions.